Yeah, so I'm just presenting this paper, but it's joint work with my co-authors, Camilo, Cruz, Gambardella, and who's at Sensi Lab with me, and Andy Lomas, who's at Goldsmiths in the UK. So in this talk, I'm going to talk about complexity. And the first question that you're probably asking is, well, what is complexity? Because there are many, many different definitions. And the specific type of complexity I'm going to be talking about is largely the visual complexity in the context of creating computational, generative, and evolutionary art. So let's delve deeper into this question. Here's an interesting image. We have this intuitive understanding of what it means to call something complex, and it's this map of Rome.
Jon,
yep.
I don't know about anyone else. I'm not seeing the slides. I've just got you.
Oh, you're right, Simon. How's that?
Yeah, much better.
Sorry, I was pressing the wrong button.
Cool.
Thank you for pointing that out. Okay, that's what happens when you go for the fancy Zoom option. Okay, so yeah, this drawing done in 1748 shows a complex image that has many different components that have some visual connection or form. And perhaps our impression of this complexity is enhanced by knowing that this is a map of a large and complex city that maybe we've experienced firsthand. We can see details at multiple scales. The connections between elements are nuanced and varying. And when we need to study the map carefully, giving it our full attention, to navigate between one part of the city and another would be quite difficult. And that's part of what gives it its complexity. This is another example. It's an image of an architectural model created in 1968, and it illustrates complexity in a different way. I'll just maybe shift myself out of view so you can see it a bit better. This is a product of a partnership between the architect Claude Perrin and the philosopher Paul Virilio, and they call themselves the architecture principle. And at first it appears deceptively relatively simple, a collection of similar oblique forms that are stacked in a repeating pattern that builds in layers from left to right. But if you look closer, you can see that there are more details and nuances to each individual form. They're not all the same, including stairways and pathways that lead between elements and contrasting areas of form and void. The layered stacking is almost generative in nature, and it suggests that the stack layering could easily be progressed, so the form would grow in scale and complexity with each iteration moving from left to right. So we're only showing the first 3 iterations here, but it suggests complexity by what it doesn't show. So we can also think about complexity in art with these 2 very well-known example paintings from the 20th century. On the left is Lucio Fontana's cut. It's a very, very simple gesture of just creating a slit in a framed, untreated canvas. It illustrates both a simple and powerful aesthetic, yet a conceptually complex interpretation that even might be considered visually simple art can evoke. And of course, on the right, Jackson Pollock, 26A, very well-known painting, shows visual complexity that rides the edges of randomness and form, asking us to consider the differences between randomness and complexity. And that's a topic we're going to look at in a bit more detail. The other question we need to consider is the relationship between complexity and aesthetics. What is the relationship between visual complexity and aesthetic appeal? Now, of course, there are many famous people who've tried to answer this question. And many people here, of course, would be familiar with Birkhoff's famous measure. And I think one of the interesting things to say about this that Birkhoff kind of got right from the beginning was that he never tried to consider this measure that would be applicable to everything in the same context all the time. But he identified 3 important phases of aesthetic appreciation. First, the effort of attention to perceive the object, which increases proportionally to its complexity. And second, the feeling of the object's aesthetic value arising from this effort, which is M in the equation. And third, verification that the object is characterized by a certain harmony, symmetry, or order, O in this case, which is necessary for the aesthetic effect. And of course, Berlin similarly looked at this relationship between pleasantness and complexity, and based on earlier work by Wundt in the previous century, devised a temporal relationship between hedonic value and arousal potential of aesthetic appreciation of an object. And of course, there are many others who've tried to formalize these relations using more recent mathematical and physical techniques, such as information theory, entropy, and even fractal dimension. So I'm just going to focus just very quickly on two, but I just refer everyone, there's two really great papers, one by Gary Greenfield and the other by Honig, who both give good overviews of the history of aesthetic measure. So I won't go into a long history here, but I'll just highlight these two contributions because they're ones that we looked at in this research. So the first one is a very well-known measure that was proposed by Machado and Cardoso that defines the complexity of an image as the ratio of the image complexity to the processing complexity, with the image complexity defined as the ratio of the RMS error of the compressed and uncompressed versions of the image and the amount of compression achieved in that image. And here for compression, we're largely talking about using a lossy compression scheme like JPEG compression. So taking an image and just JPEG compressing it. The reason that these are used is that they're considered a reasonable proxy for information complexity. And several years ago, Den Hijger and Eben used 4 different aesthetic measures in a simple evolutionary art system to see how effective each measure was as a fitness measure, including the measure above there. And they found that the measures in combination often produced the best results. So let's talk about the measures that we looked at in this research. So we looked at 10 different complexity measures, and I won't go through all of them in detail, but I'll just highlight a couple of them. They're all listed in the paper, so you can read more about them there. And maybe the other question to pose is, well, why are you looking at complexity? What's this going to do? And I think one of the reasons why we wanted to look at this was to see if they could be used in an evolutionary art system to predict how interesting or visually appealing a form might be. And of course, many other people have tried this before. Or perhaps they could be used to filter out at least those uninteresting candidates that lack some kind of visual complexity. So I'll just talk quickly about a couple of the measures. Some of them use measures of entropy, so they look at the distribution of intensities across the image. Some measures were morphological, so they basically break the image down into discrete morphological components by looking for boundaries and then just count the number of boundaries. Other measures use, as I mentioned in the previous slide, they use compression techniques to get a sense of the information complexity of the image. And one of the most recent ones was a paper that was just published in the middle of last year by a couple of physicists or a group of physicists in France, which uses compression ratios in a similar way to previous measures, but also does some pre-filtering on the high frequency spatial and intensity noise from the image before they perform the measure. And they call this measure structural complexity. They ran a very large survey with thousands of images and got good correlation between people's perception of complexity and the actual measure. But the important proviso there is that they were not running it on real images, they were just running it on synthesized images, and they were just very abstract, so they wouldn't even be considered to be art. Okay, the other thing is that we used 3 very specific data sets, and all of these are open access, so I'd encourage anyone who's doing research in evolutionary art to feel free to access any of these data sets. They're all open access. So I'll go into detail on each of them. The first one is one developed by Andy, one of the co-authors, Andy Lomas. So many people would be familiar with Andy's work. He's a very well-known computational artist. So this data set consists of around 1,700 images of evolved 3D morphogenic forms. And the important part is that each of the 1,700 forms has an artist-assigned aesthetic ranking from 0 to 10. So 0 being not very interesting and 10 being really interesting. There's also in the metadata, there's categorization, but we didn't use that for this research. The second data set is my own work from probably 10 years ago now, a little bit longer. It's only 53 images, but they're all algorithmically generated line drawings created using a biologically inspired niche construction technique. And these are all given an aesthetic ranking by me, ranging between 0 and 1, where 0 is the worst and 1 is the best. And finally, the third data set we used was a set of 2,500 evolved 3D forms generated by a differential line algorithm method. maybe one of the differences here is that the forms were used for 3D printed sculptures, but they're rendered as 2D drawings. So I'll come back to the reasons for doing this in a minute. Each form, rather than having an artist-assigned aesthetic value, it has a physically calculated complexity that's directly calculated from the variations in the 3D geometry. Again, there's details in the paper. I won't go into the exact formula that we use, but it's directly measuring the geometric complexity, not the visual complexity of the form. And here you can just see some examples of the 2D renderings on the left in A and B, and the 3D printed forms on the right. So one of the problems that you find is if the form becomes too complex, it doesn't become 3D printable. So we actually devised a fitness function that would filter out any of the images that weren't 3D printable before they got printed. So it saved us a lot of time printing them. Here's just an example of two of the final forms that we got by evolving the fitness as a the complexity as a fitness function and the printability as a fitness function. Okay, so onto the results. So what we did was to run these 10 complexity measures on every single image and then look at the correlation between the measured complexity and the artist-assigned aesthetic score in the case of the line drawing and the Andy Lomas data set. Or in the case of the 3D forms data set, it was the physical measured complexity. So I'll go through each one individually first. So the Andy Lomas data set, the important result, I guess, was that the complexity measure, information complexity measures performed the best with these. And so these are trying to sort of measure how much processing is required and how much information is contained in the image. And you can see there's a pretty high correlation. So these are Pearson correlations. The p-values are all very small, so we can be pretty confident that they're accurate. 0.873 was the result achieved for the Andy Lomas data set. Let me just move on to the next slide. Here's two plots. The plot on the left shows the relationship between the complexity measure, so the best performing complexity measure, and the score. And you can see that there's a reasonable linear relationship, but there are some outliers and a reasonable amount of variation. The reason why they're shown in bands is because the artist-assigned score in this case was an integer. It wasn't a floating point number. And on the right, there's the relationship between the Machado-Cardoso measure and the more recent Lackel information theoretic measure of algorithmic complexity. And you can see that there's a strong correlation between both measures. And it's easy to see why one gets a slightly higher linear correlation score, because you can see that the relationship's non-linear between them. So I think the takeaway from this is that actually algorithmic image complexity measures are a pretty reasonable proxy for Andy Lomas's aesthetic score that he gives his forms, and that they would be pretty good for helping him find or searching for forms that he would give a high aesthetic score to, or at least to reject the ones that don't have a high aesthetic score. Here's the results for the 3D forms data set. And while it's not as impressive as the previous results, there's still high correlation, this time between the structural complexity and the measured physical complexity. So you recall that the structured complexity measure filters out high frequency spatial and intensity detail. And one of the tricks that you have to do with this measure is that you need to work out the appropriate values for the coefficients for this filtering. And in the original paper, the authors used different values for different data sets, but didn't really say how they arrived at them. I think apparently they reached them through trial and error. So we did a similar approach, and we found that there's a reasonable latitude in varying the coefficients. And they're largely related to the image resolution that you're actually measuring. So there is a factor about how high resolution the images are that you're sending to this measure. But again, the correlation is pretty good, 0.774. Here you can see the relationship between the score and the structural complexity. Again, a clear linear trend is visible, but there is a reasonable amount of variance. One surprising result, however, was how really poorly the fractal complexity measures performed. So some of the measures used fractal dimension, and this was really quite unexpected because there are a number of publications previously that have done large-scale tests with people's, impression of aesthetics and complexity. And they've been reasonably well correlated to things like fractal dimension, or at least sort of having a sweet spot for the fractal dimension around 1.35. So the plot on the right shows the relationship between the score and the fractal dimension measure. This measure, we calculate it using a box counting method, which is a very common method to do fractal dimension of an image. And we fitted that to a Gaussian curve with the peak at around 1.35, which, again, according to the literature, is the sweet spot for fractal dimension being most aesthetically pleasing. And again, you can see that there's some clustering around the sort of medium complexity area. So we had a look at the individuals that were getting this score, and many of them had branching structures in them, indicating that this was actually a better measure of if something was branching or not, rather than if it was actually physically complex. Okay, so the last data set, these are the results for that. That's the line drawing data set. And interestingly, in this data set, the morphological complexity measures gave the best results, which is kind of unsurprising because they're basically counting the number of distinct morphological features using contours. And so, of course, because they're line drawings, they're going to find lots of contours, and the more contours they find, the higher the complexity score. But again, the correlation is fairly mild, 0.565. It's also interesting to observe here that the algorithmic complexity measures perform the worst of any of the measures. So after running this experiment, we tried an additional measure on the data set, which was to measure the skew of the image. And this is basically, it measures how skewed the intensity histogram is, and that gave a slightly better result, 0.583. This is not really, again, surprising because these drawings are based on niche construction, which tries to maximize the diversity of high and low density regions in the drawing. It's an agent-based drawing method that's kind of evolutionary, and the individual agents evolve to try and make drawings that are dense in some parts and sparse in other areas. So it seems reasonably reasonable that this measure performs better than the other complexity measures. Because the data set's quite small with only 53 images, I can actually show you all of them on a single slide. So on this slide, we see the same data set, but ordered in a different way. So on the left is the data set ordered by my personal aesthetic scores for each of the images. And so it's ordered from left to right, top to bottom. So the one on the top left is the least interesting for me, and the one on the bottom at the rightmost end is the most interesting. For the slide on the right-hand side, it's ordering via structural complexity. So it's this recent physics measure of image structural complexity. And you can see that the increasing visual complexity is kind of there, but it's very different. And there's some sort of outliers. That's ones that I rated very highly are actually rated low in terms of the structural complexity. So this might have something to do with the high frequency detail being filtered, but it does demonstrate that just naively applying these measures isn't going to necessarily work or actually be that useful. Okay, so a bit of discussion. What did we learn from all this? I think one of the first questions is, should you use these complexity measures in your generative art system? Are they going to be helpful? And I think based on our experiments, the answer is probably a qualified, that depends. So I'm going to sit on the fence a bit. First, these measures, I should say the pros, are relatively quick and easy to compute. So you can compute them very, very quickly. You don't need a bank of GPUs or TPUs like you do for deep learning, for example. The next point is that they work on 2D images, so they're agnostic about the generative system or the method of generation that you use. As long as you can generate an image of what you're interested in, you can apply one of the measures, so that's a positive. And our findings indicate that there's no single best measure, but if you choose a measure carefully that's appropriate for the kind of work that you're doing, it can act as a reasonable proxy for human aesthetic judgment. So it can be useful as part of a fitness measure in an evolutionary system or as a filter in a generative system. And this could end up saving you a lot of time and hence potentially give you better and more interesting results. But as the old paper, and the old saying goes, there's no free lunch. And we've only tested 3 very distinct and specific data sets, so we can't draw any universal conclusions from the work that we've done so far. Now, you might ask about, well, what about other methods? So in a paper we presented at EvoMuseArt last year, work by myself and Andy, we did use deep learning to do pretty much a similar kind of thing to predict how much a neural network could learn an artist's individual aesthetic evaluation. And we did get better results. You can see here, we got around about 87% accuracy, which is a little bit better than we could get with just the naive complexity measure. But the downside of this, of course, is that it requires a large amount of training. So you need to train the neural network first, and that it must include artist-assigned aesthetic scores and categories, which is very time-consuming to do. So to develop this data set took Andy months and months of time evolving these forms, assigning an aesthetic score and a category to them. And it's just fortunate that we have access to that much data to do the training. So it's not a trivial task. And the other issue, which is very topical at the moment, is that this training requires, a large amount of GPU or TPU resources to do in reasonable time. So your electricity bill and potentially your environmental impact could be quite high to do this. There's also a factor which is important as well, and that's how much of aesthetic judgment and aesthetic experience comes only from the object being judged. And because that's the only thing that we're measuring. We're only measuring what we find in the produced artifact or object. We're not measuring anything else. So this is a really great paper. I'd encourage anyone who hasn't read this paper to have a look at it. It's from a group of psychologists led by a German researcher leader. He's been working in the area of aesthetic appreciation and judgment for decades, so he knows a lot about how humans come to form aesthetic judgments. And this is the reasonably recent version of his model. I think it's from about 2014. And it's drawn from a lot of research in psychology and neuroscience about how aesthetic judgment is formed. So perceptual analysis and hence measurable properties of the object, such as complexity, symmetry, and so on, which is what we're looking at, are only one part of the overall model. You can see that they're just in one box in a much bigger set of situations and knowledge and circumstances. So it also includes the observer's prior knowledge, cognitive mastering, domain knowledge, and the viewer's affective state. So this is one of the reasons why in this paper, we used individual personal aesthetic evaluations rather than collective evaluations. So we didn't go and show these images to a large group of people and use the average rating that they gave them, because the aim was to keep these external non-object contributions to aesthetic experience constant for every evaluation. So we make the assumption that the artist who's doing this has the same background knowledge and previous experience throughout their assigning of the values, and that there are, this might be naive, but their affective state is more or less the same. And this is kind of backed up by some other recent research. There's a really interesting survey paper by Skov. He recently summarized the aesthetic appreciation research from the perspective of neuroimaging research. So it's just a big survey paper about all of the neuroimaging research into aesthetics. And his key finding was, it's worth repeating, aesthetic appreciation is not a distinct neurobiological process assessing certain objects, but a general system centered on the mesolimbic reward circuit for assessing the hedonic value of any sensory object. Another important finding was that hedonic values are not solely determined by object properties. They are subject to numerous extrinsic factors outside the object itself. So basically what the neuroscience research is saying is you can't just look at an object and say how much someone will give it an aesthetic value. Okay, so just to conclude and talk very quickly about future work, it seems clear that the research that we've done shows that aesthetic judgment, or the research that others have done rather, shows that aesthetic judgment is not the sole property of an object or image. So any aesthetic measures we devise need to take this into account. Our study found that complexity measures have some benefit if chosen appropriately, but cannot completely replace human judgment or discretion. One of the things that we're interested in doing now is undertaking a study. We're actually starting this study soon, so hopefully everyone would love to participate in this. It aims to see how the audience's judgments about complexity and aesthetics correlate with an artist's personal ones. So we're going to take these data sets and allow people to basically give them their own aesthetic judgment, and we'll see how they compare with the original artist's aesthetic value. But I think the whole idea of complexity is still has a lot more nuance and to use the cliche, complexity about it, and what it means for our understanding of what makes generative art appealing. But it's clearly it has some important role, and it's something we're still finding out. So thank you. That's the end of the talk.
Okay, thank you very much. So we have a moment or two for a quick question. Does anyone have a question? If so, can you put your hand up? I've got a quick question. Is there a correlation between any sort of formal correlation between these measures? Are they free to roam in different dimensions, or are some of them sort of mathematically correlated with each other?
Yeah, so probably because I put so much information on the correlation slides, you didn't have a chance to look at all the figures, but the correlation values show also the correlation not just between the complexity measure and the artist score, but the correlation between each measure. And yes, all of the information complexity measures are generally highly correlated. The fractal measures are correlated to each other. But interestingly, depends on the data set, whether the groups of measures in the different categories are correlated to each other. And in some cases they are, and in other cases they're not. So I guess that's kind of equally as interesting finding, is that these measures, they work differently for different kinds of data. And the reason we chose these data sets was because they're actual real examples of generative art. They're not made up systems or just toy or play systems. They're actual artworks that people have exhibited and sold, and so they're kind of ecologically valid. So yeah, there's correlations, but they vary depending on what it is that you're looking at. There's no uniform correlation between the measures.
Any other quick questions? So
I think there's one in the chat.
Yes. You want to answer
Shall I
that?
just quickly read it out? How would the findings apply if the measures were calculated for the 3D artifacts rather than their 2D images? Yeah, good question. Well, firstly, you can't really apply them to 3D images because they're designed to measure, they're all specifically designed to measure image complexity. So we did, in the 3D forms data set, we did set out to measure the geometric 3D complexity of the object. So we came up with our own measure. It's based on a lot of prior work. And I guess the fact that it correlates reasonably well with the visual complexity that you see and also the measured complexity indicates that it's a pretty reasonable measure. But because these measures all are designed to work on 2D images, you can't just apply them to 3D images. One other quick point I'd make too is that also the way that people evaluate these. So when Andy Lomas was developing his data set, he wasn't looking at the 3D models, he was looking at 2D renderings of the 3D model. So he was making his aesthetic judgment on the 2D image, even though it's a 2D image of a 3D object, he was judging it based on the 2D image. And so that's why we're doing them on the images and not on the 3D models.